Today it's time for part 2 of Fraunhofer diffraction. We're going to look at multiple slits, the diffraction grating, and then we're going to look at the rectangular aperture and then the circular aperture, and introduce a Bessel function when we do that last one, and that's a quite advanced mathematics there. And we'll make a connection between the aperture, the light at the aperture, and the Fraunhofer diffraction pattern as being a Fourier transform. You might remember when you did hear the rectangular pulse, which you could think of as a narrow slit, that you have 0 for the function and you have something and then you have 0. You got the sinc function. You got sine of something over something. And that's what we got for the single slit. That's the Fourier transform. The Fourier transform is on the wall. It's on the screen of what the slit is. And then you can imagine, instead of having a constant brightness on the slit, say it varied, there's some function that modulated that brightness, then when you look at the integral and have that factor in there, you're actually taking the Fourier transform of that brightness function at the slit source. Fascinating stuff. Let's get on with the show. Chapter T. Fraunhofer diffraction II. T1, the diffraction grating, or multiple slits. And diffraction gratings can have hundreds of slits, 1,000 is you can find easily, and more. So we're going to do multiple slits, in the book I have 7 of these, but each of these slits have B for the size of the opening, the width, and the distance from the center to the center is A, like we did before. Now let's consider this to be 0. U is equal to 0. And we're going to go up with U like this. And we're going to look at an integral from 0 to B. And then this next one, if we come up here, this is also A. Since A goes from the middle to the middle, if we shift both down by B over 2, you still have A. And we did the 2 slits before, 0 to B, and then A to A plus B. But see, if we go to the beginning of the next one, that's another A. That's up. And let's do another one here. So if I have 1, 2, 3, 4 slits, notice I only have 1, 2, 3 A's, because I'm going to integrate that last one from 3A to 3A plus B. So in that sense, we could say that this is, if that's the nth slit, like that's the 4th one, then 1, 2, 3, to get to this point is n minus 1 times A. So there's 3 A's to get there. but there's 1, 2, 3, 4 slits. Now we can build up to this fairly easily because the single case we had for the single slit, we had the electric field amplitude at the screen, CH e to the I, K, R naught. We're simply bringing down what we had before, minus B over 2 to B over 2, e to the I, K, U, sine theta, du. And this was a constant here, like E naught over R naught. And when we did that, we got the answer, and this was one slit, so we call this diffraction formula. We got sine squared beta over beta squared, where beta is 1/2 KB sine of theta. For the double slit, we had to do two integrals, and let's write the CH on the left this time with the e to the minus IK R naught, so I can focus on the integration. Then we went from 0 to B and had the same integrand. And then we went from A to A plus B. Did that integral. And then what we got for this was the irradiance or intensity at the central point on the screen, and then there was a cosine squared alpha and a sine squared beta over beta squared, where now still had your beta definition, but we added one for the alpha, Ka sine theta over 2. And this was the interference term that gave us cosine squareds. So down at the bottom here, it'd be like your 0 point, all of them are positive, all those places. And then this was the sinc squared, which would modify the interference pattern and kill some off. They were called missing orders. Like this is the central point, like order 1, order 2, and some would be missing. So it's kind of obvious what we have to do here. We just have to keep adding more pieces to this, you know, go from then 2A, say, to 2A plus B. And we're going to use the same result we did before. Say before we had EP over CH e to the minus I K R naught. That was equal to the integral from minus B over 2 to B over 2 e to the I K U sine theta du. And we're going to do the same thing that we did for the double slit, but continue along. So we're going to integrate from 0 to B, and then from A to A plus B, and then from 2A to 2A plus B, and so on. So for the multiple slits, or multi-slits, we're going to have here the series of integrals. 0 to B, e to the I K U sine theta du, plus A to a plus b, e to the I ku sine theta du, and then 2a to 2a plus b, e to the I ku sine theta du, dot, dot, dot. And the last one is going to be from here. This is going to be 1, 2, 3, n minus 1 a to that point plus a. So here's n minus 1 a, and then we're going to n minus 1 a plus b. And this takes care of the all the slits where n can be some general case. I have 4 listed here. And notice there are here 1, 2, 3, 4 integrals going on. In general, be n integrals. Okay, so integrals are easy to do. They're all going to have e to the I ku sine theta over I k sine theta. So if I take a derivative here, I get the same thing back and pop down the I k sine theta, which cancels there, and I get what I'm supposed to, and that's 0 to b, plus same thing, write it out again, and that's going to go here from a to a plus b, and then same thing, I ku sine theta, I k sine theta, and that's going to go from 2a to 2a plus b. And then same thing here at the end, e to the I ku sine theta over I k sine theta. And now we're going to go from n minus 1a to n minus 1a plus b. So there you have it, all the integrals. So first thing I'm going to do here is these I k sine thetas, let's get those over to the other side. So I have here I k sine theta e p over ch, e to the minus I k r naught. And now I just have the exponentials. And the exponentials here we're going to look at, put into b and then subtract the lower one. So this is I k b sine theta minus, when you put in the 0, you get e to the 0th power is 1. And then the next one is e to the I k, this is going to be a plus b sine theta. And then when I subtract, put the a in there, I get I k a sine theta. Then the next one is going to be e to the I k. Now I have 2a plus b. 2a plus b up in there. And I'm going to subtract, well, I'll put my sine theta in there. And then I'm going to subtract e to the I k 2a down at the bottom there. And then the last one, e to the I k, this is going to be n minus 1 a plus b sine of theta minus e to the I k n minus 1a sine theta. And that's the last one. So like we have them all. Very, very similar. The k, b, and then the k, a plus b, see? And then the lower limit a. So they all come out very nice. And now we're going to do a trick. What we're going to do next is we're going to do some factoring. We're going to leave this first one alone. But here, I'm going to pull out the second term. So this is e to the I k a sine of theta. If I pull out that second term, then this first one is going to have e to the I k just the b, because I pulled out the A one, and then this is minus 1. So that's the same as that. And then here, if I pull out the K with the 2A sine theta, then I'm left with just the B1 and minus 1. And then for the last one, I pull out e to the ik n minus 1a, so that I have here ikb sine theta, and then that's, oh, it needs sine theta, it's easy to leave that off, minus 1. So I have one of these everywhere. So we're going to factor that out. So if we factor that out, e to the ikb sine theta minus 1, like pull that out of all of them, then you're going to have here, well, 1 for the first one. This is going to be 1. And then for the next one, we're going to have this thing, e to the ika sine of theta. And for the next one, we're going to have e to the I2 ka sine theta. And dot, 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 the last one, e to the ik is going to be n minus 1 a sine theta. And you have this common factor. Now this is a series, a geometric series of the form, and if I use math notation where they use the r to represent the factor, you multiply by 1 times r squared, r cubed. You're multiplying by r each step until you get to the r to the nth power. Because that's what we're doing here. It's like this, there's one of these here. In fact, the r is e to the I ka sine theta. And then if you multiply 1 by this, you get this one. And then if you multiply again, you get, then the exponent's going to add, you get 2 up there, and so on. And here's how you can find what that sum is. Multiply by r, you get then r plus r squared plus r cubed plus r to the 4th plus dot, 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 r to the n plus 1. And now we're going to subtract. If we subtract these, we'll have Sn minus Rsn. And notice that all these r's cancel, these powers of r's cancel, and I'm left with the first one and the last one with the minus sign since I'm subtracting. So, you know, these cancel, these cancel, these cancel, these cancel. So I have 1 and then minus the one that doesn't cancel, the n plus 1. So that means Sn with the 1 minus r is 1 minus r to the n plus 1. And that means Sn, I'm going to write this where I have here, we can write this 2 ways. 1 minus n plus 1 over 1 minus r, or we can multiply top and bottom by 1 and just flip these and do that. I'm going to prefer to use the second version. So notice that in our case, the n, the little n, is equal to n minus 1, because that's what I have, you know, as the last one. I have n minus 1. This is the first one, and this is the r. Say that's the r squared. So then I can get this sum to be, and maybe we here write it out, we write everything out again. So ik sine theta EP over ch e to the minus ik r naught, that equals, we're going to have this term here, factor, so this is going to be e to the ikb sine of theta minus 1. And now for all this stuff, we're going to use our formula. It's going to be r to the n plus 1, and here is r is going to be I, K, and remember little n plus 1 is capital N. So that's nice. This is just n, a sine theta, and then minus 1. And then in the bottom, we have the r e to the I k a sine theta minus 1. So this is what we have. This has three things that have this form, where we have e to the I, say, some phi minus 1. Like we have this like three places where we have e to the some I like something minus 1. This is e to the I phi over 2, e to the I phi over 2 minus e to the minus I phi over 2, which we can check. Multiply this, exponents add, you get this. Multiply this with that one, the exponent's going to be 0, so it's going to get you to 1. And this is 2i sine of phi over 2, using Euler. So now we can apply this 3 times in these 3 places, and if we do that, we will get e to the minus I k r naught. We will get, for the first one, well, first of all, you got to pull this out. So you're going to have this thing with the 2 in the exponent. So we're going to have e to the I k b sine of theta over 2. And then we're going to have the 2i sine of the phi over 2. So that's going to be kb sine theta over 2. All right, like that. So that's the first one. Then over here, we'll have this pulled out, dividing by 2. And then we're going to have here 2 times I, and that's going to be the sine of what's in here, the k n, big N, a sine of theta over 2. And then we divide, for this one, e to the I k a sine theta over 2. And that's going to be then 2i sine ka sine theta over 2. So there we have it. Notice that these 2 i's here are going to go out. And notice also that this I will go out with that I. So I'm going to write this again with those cancellations. And if we do that, make one more thing. We're going to call this alpha times n, because we want this one to be the alpha. We want alpha to be ka sine of theta over 2, and we want this to be the beta, kb sine theta over 2. We did these kind of things before. So if we do that and pull it all together, we'll have over here, we'll have k sine of theta EP over CH e to the minus IK R naught. This will be e to the I beta. There'll still be a 2 floating around, sine beta. Over here we'll have e to the I n times the alpha times the sine of n alpha, and then we'll divide by e to the I alpha and sine of alpha. Now that's starting to look really nice. And I would like to now write EP by itself on one side of the equation. EP is equal to CH, bring that on the other side of the equation. And we're going to have a 2 floating around. So before I mess with that 2, let me do this. I'm going to divide by K sine of theta. And here, this 2 if I divide by 2 here, when that flips, I'll have the 2 upstairs. And if I put a b here and a b there, then this will be a beta. So the b's cancel, and the 2 flips up to give me that 2. That 2's accounted for. And then I'm going to have e to the plus I k r naught. Then it'll be e to the I beta. And there'll be, let's put the e to the I n. Oh, by the way, look, there's one of them there. So this is n minus 1. E to the n minus 1 alpha. And then we're going to have the sine of beta and the sine of n alpha over the sine of alpha. Notice that this pops up. This is the area of one of the slits. Each slit has width b and height h. Isn't that cool? See that there? And then when we go to the next step for the irradiance, we're basically looking at, EP star divided by 2. And when we do that, when you star the thing, these become minus signs, the i's, and then when you multiply them, they go away. So they get 1. So this is going to be c squared, a squared, over 2, and I'm going to have the sine squared beta over beta squared coming from over here, and then the sine squared and alpha over the sine squared alpha. But we really want this in terms of the I at 0 radians, or 0 degrees. So we look at L'Hopital's rule, and we did that before when we looked at sine of beta over beta. And by L'Hopital's rule, when you take the derivative, you get cosine of beta, and then here you get a 1. And that's going to be 1 when the beta equals 0. And that corresponds to theta equals 0. When theta equals 0, you see, here's your alpha. Let's go ahead and put the 2 there. So the alpha is Ka sine theta over 2. So theta is 0, alpha is 0. If beta is 0, that goes along with theta being 0. All right, so that's at the central point at 0 radians. But what about the sine of n alpha over the sine of alpha? I'd rather work with them not being squared. It's easier. So we're just working with them without being squared. So L'Hopital's rule says this is n times the cosine of n alpha, and this is the cosine of alpha. Now, when you put in alpha to be 0, you get n. Whoa. Which means we can fix this. I will be equal to I naught if we do this trick. Then sine beta over beta, keep that the same. That's the diffraction coming from the individual slits. And then have sine of n alpha over n sine of alpha, and square that. Now here, when beta is 0, when theta is 0, beta will be 0. That's a 1. And here, when alpha is 0, then this will be 1. Because if I put the n with the sine of alpha down there, then this becomes a 1, goes to 1. So that's the answer. This is our answer for the diffraction gradient. Isn't that cool? Very nice. Okay, we want to check the max minimum. We already did this one. This one has that nice function that does something like this. And the interference pattern had lots of wiggles in there, and this would kill some off. So here, let's look at where these would have like your maximum. And here, this is interesting because your sine of n alpha over n sine of alpha, if you use L'Hopital's rule on this thing, you're going to get n cosine of n alpha, and then n cosine of alpha. Now we did that when alpha was 0 and, you know, got our max, we got like 1. But guess what? If the alpha here is some multiple of pi, then if you put in pi, cosine of pi, or 2 pi, or 3 pi, or 4 pi is plus or minus 1, and the cosine of here, some multiple, same thing. See, this n is a number, like 1, 2, 3, 4, 5 will be a big number. So when you have n times n, you still get a number, and to be an integral multiple of pi's. So this is going to be going to 1. So that's where the principal maximum are. And so this is called the principal maxima, and they occur when here, you know, you can think of n, you can even put in 0 in there, plus or minus 1, plus or minus 2, etc., because you have them on either side. These are the principal maxima. Now for the secondary maxima, we're going to consider the sign maxing out at 1 or minus 1. All right, then you square it and you get 1. So that's going to occur when n alpha is equal to like pi over 2 or 3 halves pi. So let's say this is some p times pi over 2 where this is odd. So that's going to get the sign to be maxed out. So let's look at the sign here of n alpha over n times the sine of alpha. And I'm going to put in here p pi over 2 and then n sine alpha. Now the alpha would be p pi over 2n, because the alpha we're going to divide by n, p pi over 2n. And if you look at this, n is going to be large, like very large, like even 1,000 or more. So what happens here is that you're looking at, we can go ahead and make this, we can make this approximation. We have the sine of p pi over 2, and then down here we have n times p pi over 2n. In other words, the sine of theta is theta. This top part's going to get you a 1, but this bottom part, this is going to cancel, and here 2 is going to flip upstairs, and then you'll have p times pi, all right, where p is like 1, 2, 3, 4, 5. So if p is 1, this is still less than 1. But if p is like 20 or 30, it's going to be a lot less than 1. So really these max are not the principal ones. The principal ones are the others, you know, where you have the case where alpha is pi times n. So let's look at some of these. Let's look here at the situation. And by the way, you had to square that thing anyway, so that's even worse if that's less than 1. You know, if that's 2 over pi, 2/3, and you got to square it. That's the first one. So then if p is 100, very, very, very low. So here you have diffraction pattern for the one slit. That's the beta kicking in. Here is the double slit, where the beta factor is this envelope, and then the alpha factor in there. 3 slits and 5 slits. Nice. And here we have nice example of the diffraction pattern with 1 slit, 2 slits. See the interference kicking in and the modulation and the missing orders. And then here, look at that, with 7 slits. And here with 150 slits, look at that nice pattern. This is our diffraction gradient. And it's modulated with the diffraction pattern, which will kick out some orders, knock out some orders, missing orders. That's very nice. Notice that if n should equal 1, you would get then this would go away, and you would have the case of just diffraction, because if this is n is 1, you have sine of alpha over sine alpha, it goes away. So that would mean you would just get this piece, diffraction. if n is equal to 2, then you would have the diffraction piece there, but now you would have sine of 2 alpha over 2 times the sine of alpha, and this is 2 sine alpha cosine alpha. We had looked at that earlier, that trig identity. In fact, we derived it. So that means this will cancel this, and the 2 will cancel the 2, and you'll have here cosine of alpha squared. This is squared. And this is exactly what we had for the case of the 2 slits. So nice diffraction and the interference. Now we go to T2. The rectangular aperture. Now for the rectangular aperture, let's go ahead and sketch something here where we're going to have some width b and now some height h. And we're going to go way over here to a screen. And let's call this point here, let's call that point there x, y, z equals 0, 0, 0. And this is z away over there. We also call that r naught. That's at this point. And here, if we have a coordinate system where, say, y is up, because this is z, and then x would be in this direction. If I have x in this direction and y going straight up, if I have my j hat straight up and my I hat going into the page, I cross j is k going to the right. So this coordinate system is a right-hand system. This looks good. And here, make myself a little box here. I want to take a point here, and probably should be using a ruler for this. This is not good. We will resort to the picture in the book since this is quite hard to sketch. Okay, so the origin is there. Out here is the point z out, like the whole plane here is z out. And then we have x and y. And these are the coordinates we have to integrate over, the u and the v, to integrate over this region. And this little patch goes off that our point's going to be there, and that's r. But I wanted to also show you the distance up from the center and call this phi, so that the sine of phi is going to be y over the r naught. Okay, y divided by the r naught. The r naught is, this is taken to be the same there. So it's like the tangent and the sines are the same, very far away. And then here, if we go in the x direction, then the sine of theta is x over r naught. Now this is not your standard spherical coordinates now, just defining these angles as convenient. So I need this thing, this r, in the formula, and we'll go ahead and have this to the side as we look at the general formula for the point P. What we want to do is we want to have some constant there, integrate over the area, e to the I k r dA. But what is this r? Well, this r is now easy to get because, see, this point that's up in here is going to be defined by u, v, and 0z, because you're not going anywhere out here. So it's just u and v, because that would be your x direction is into the page, and up is your y. So all I got to do is subtract these and square them. So that's what I'm going to do. I'm going to take x minus u, square it, y minus v, square it, and z minus 0, and square it. So just take the x minus the u, the y minus the v, and the z minus 0 squared, and that'll get me, take the square root, that's get me this r. And that's the r to have to make this move around. I have to integrate, making the u and v move around, all around there. And that's what I put up in there. But if I look at this and work this out, I get x squared minus 2xu plus u squared, and then I get a plus y squared minus 2yv plus v squared, and then plus a z squared. Now, the u squares, and these u and v are very, very small. They're going to be in this plane in here, and they're very, very small. So what we're going to do here is neglect those, throw those out, and x squared, y squared, and z squared gets you up to the point P. So this is going to be the square root. So that gets me x squared plus y squared plus z squared minus 2xu minus 2yv. This x squared plus y squared plus z squared, and take the square root, it would actually be going from the center here up to that point. But we're going to consider that to be r naught squared in our approximation. So we have then r is r naught times the square root of 1 minus 2xu over r naught squared minus 2yv over r naught squared. Let's check this. If the r naught goes inside, this becomes the squared. That's what this is. And this will cancel, and you'll get that. And the r squared will cancel, and you'll get this. And this is going to be now r naught something 1 minus something small to the 1/2 power. And that means we'll have 1 minus 1/2 of epsilon. So this is 1 minus the 1/2 is going to be xu over r naught squared, and yv over r naught squared. And this is going to be r naught minus x over r naught u minus y over r naught v. And guess what? Y over r naught's the sine of phi, and x over r naught is the sine of theta. So this is r naught minus u sine theta minus v sine of phi. No surprise, because we've seen that before. If we now use our formula, EP is C, now I'll show you how we've seen that before. If we do this, we're going to get E to the R, this is going to be I, K, R naught, and this is going to be E to the minus IKU sine theta, and E to the minus IKV sine of phi over the area. And we've seen this one before, where we did the integration for this narrow slit. And now we see we have two integrations to do, and they're multiplied by each other. So what we can do here is we can take EP, which is E to the I K R naught, and some constant floating around in the front. Then what we'll have here is the integral from minus b over 2 to b over 2. This integral is going to be for, if we look at this here, we're going to go here, integrate from minus b over 2 to plus b over 2 for the u, and then for the v, minus h over 2 to plus h over 2. So we'll pull the u one out, minus ku sine of theta, and that would be then here the du, and then from minus h over 2 to h over 2, we have e to the minus ikv sine of phi. Now, you might want to worry about this and say, wait a minute, last time we had a plus sign here, now we have minus sign. What's the deal? Well, if you let u go to minus u and v go to minus v, then these become plus signs. and these integration limits flip. But if I flip them back and bring in two minus signs, they cancel. So since this is a symmetric region I'm going over, it really doesn't matter. So don't worry that before we had a plus sign there, we get the same result. In fact, if we do that trick, we can just simply write this as the same result. C e to the I k r naught minus b over 2 to b over 2 e to with the plus sign. All right, like we had before. Du, we did that integral. See, so we're basically finished here because we just have two of those. E to the plus ikv sine of phi dv. And we already did this. We did this and got the answer. When we did, our beta definition, so here with the beta definition, we had kb sine of theta over 2. And then now we'll make here an alpha definition for the kh sine of phi over 2. And then we have the answers. See, because this was sine of beta over beta. And this is going to be then the sine of alpha over alpha. So the answer that we're going to get for the I, sum I naught, we're going to get sine, put the alpha one first, alpha over alpha squared sine beta over beta squared. Isn't that cool that we could arrive at the same result for this single slit by looking at this thing far away, doing a problem a little bit differently? But the bonus is, by doing that, we have a bonus. Because if you look at what this is doing, let's go back up to here, and let's pull this out. If you look at what this is doing, this is basically, and I'm going to put back here the u sine of theta. I'm going to put down here for the sine of theta, I'm going to put back here, leave the u, but for the sine of theta, I'm going to put the x over r naught back in there. All right, so we're looking at this. We're looking at some integral here. We're going from, say, minus b over 2 to plus b over 2, and we have e to the minus I k u x over r naught, and that's du. So we're integrating at the source. I want to throw in here, instead of having uniform lighting, I'm going to have some, say, function f of u where the light could vary. Then this is the Fourier transform that we looked at earlier. And so this is going to give me some function of x at the screen where I integrate over things at the source. So see, this is of the form e to the minus I k x. I'm going to absorb that r naught into k because this is the abstract form. Well, the formula for Fourier transform have f of u here, and this is du, and I could even put a 1 over square root of 2 pi in there, and then do the integral from minus infinity to plus infinity because the source would be 0 there. So this is the Fourier transform. So this is amazing that what you see, that's the Fourier transform of a constant function rectangle. And we saw the Fourier transform of the rectangle, the pulse. Remember, we did this pulse for our homework, and that pulse had then, had the sinc function, and that sinc function with its sine of x over x, in this case it'd be a sine of beta over beta. That's the Fourier transform. You're looking at the Fourier transform of the source on the screen. Amazing. Notice the beautiful two-dimensional effect here. T3, circular aperture. For this one, we're going to go to the book, and we have the same diagram down here that we did for the single slit. Same physics. Only difference is here, and this should be turned sideways here. We're going to look at a strip here because it's not a one-dimensional integral, it's going to be over 2 dimensions. So we look at the strip, and that strip for our area, see, that's going to be the strip length times the du. Well, what is that strip length? Well, if you look at this thing, you have a radius A, you got your u variable, and this is half of that strip length. But see, this is going to be the square root of a squared minus u squared. And then I'm going to need 2 of them because my dA is going to be that strip. It's going to be 2 of these, a squared minus u squared du. So all I have to do is the same integral that I did before, the same setup as before. It's just that for the, instead of just having the du, I'm going to have this because I have the 2 dimensions. So let's write that out. Okay, so let's write that out over here. That's going to be our setup. EP is going to be some constant over the aperture, e to the I k r dA, and that's going to be equal to C, and we're going to integrate from minus A to plus A, and this is going to be e to the I k r naught. This is the exact same thing we did for the single slit in terms of what the integrand is. It's just that we're going to have here this extra factor due to the strip. All right, and that's going to actually cause a problem. We're not going to be able to do the integral, but you'll see in a second. So what we'll do here is, first of all, we'll pull out the, with the C, we'll pull out the e to the I k r naught, which we had done before, and go from minus A to plus A. And how about if we pull out an A also? Let's do that. So we'll have here e to the I k u sine of theta. And if I pull out an A with that 2, then I'm going to have the square root of 1 minus u over A, that quantity squared. All right, so put the A back in, it goes in as A squared, you get this, and then A squares cancel, you get U squared. Now this suggests that we let S equal U over A, change a variable, so this will look simpler, and then ds is du over A, and then as S, well, as the S, you can see that when the U goes from minus A to plus A, which is its natural range, then the S is going to go from -1 to +1. So we can just put those down together just so we can see them. The U is going to go from minus A to plus A, and then since we're dividing by A for the S variable, we go from minus to +1. So if we do that, for the point, we get a 2, C, A, e to the I k r naught, and then we're going to integrate from -1 to 1, e to the I k, and then here, what is u? Well, u is A times S. So this u is A times S, and then there's a sign up there also. And then here, we'll have the square root of 1 minus S squared, but what's the du? Well, the du here would be A times ds. Now I like this, that A hits that A, and you get that area again, like pi r squared kind of thing, or pi a squared. So EP is here 2ca squared, e to the I k r naught, and now we go from -1 to 1, e to the I. Now here's another thing I want to do. You know how we like to do this, we do this often, where we like to these definitions, you know, K, H, sine of phi over 2, you know, beta is K, B, sine of theta over 2. Well, the B is your width, this is the height, you know, when you had the rectangle, and if you want to do the same thing, you should use diameter. Same idea. So the diameter is 2a. So what we'll do is we'll make a definition, and to pick an angle, since I'm using S, I'll pick the sigma as the angle. So the sigma would be K times 2a sine of theta, and this is going to be over 2. So those 2's will cancel, and the sigma is going to be Ka sine of theta. So the Ka sine of theta part is going to be sigma, but the S is there. So I have to have the S there, and the rest is going to be the sigma. And then this is 1 minus S squared. The A already has been pulled out, you know, ds. This integral cannot be done. So we're kind of at a standstill. So if we look at what we have so far, EP is some constant C prime. We'll absorb everything in there together. And that's from -1 to +1, e to the I, S sigma or sigma S, it doesn't matter which way you write that, 1 minus S squared ds. And this is one of the Bessel functions of the first kind. In particular, this is pi times J1 of sigma over sigma, Bessel function. Notice that this is going to be real, because if you were to write this as a cosine of sigma s plus an I sine of sigma s, this is over an even symmetric interval, and this is an even function, so that means the odd function is going to be out. It's not going to be in there, so this is going to be real. Of course, we don't worry about that, because when we do this EP, you know, EP star, we make things real anyway, for sure. But I just wanted to point that out. And then here we're going to look at this thing. J1 does this. Wild. And then J1 divided by x, because see, this is of the form J1 of x over x. You then have this. And notice that the first minimum occurs, we're going to be squaring this thing, but here, look at this 0. This is your coordinates here. This is 2, this is 4, this is the 0 line. This is a little bit less than 4. So that means in our diffraction pattern, we're going to have a circle where when the value for sigma is around a little less than 4, it's going to be the end of the circle. It's going to go to 0. So this is actually here, actually this is going to be 3.832. But I would like to mention one more thing to get our I as a function of theta. We want the I naught. What we need here is, because we're going to be squaring the J1 sigma over the sigma, we need to put a 2 here, because when the J1 over sigma, you put in 0, you get a 1/2. This is 1/2 up here, this is 0.5. All right, so if that's 1/2, then the J1 over the sigma, when you're at the angle 0, it's going to be 1/2. That has to cancel this 2, so you have the intensity at the center. So that's called normalization. So that first 0, though, is going to occur when you have 3.832. In other words, this is Ka sine of theta, which is the sigma. All right, that's what this is. and this K is 2 pi over lambda. So that means here, and if I want, I could say, if I want this in terms of the diameter, this is d over 2, all right? So we clean this up, we get pi d over lambda is equal to 3.832, and there's a sign that goes with this left-hand side. There's a sine of theta. So that means d times the sine of theta. If we bring the lambda on the other side of the equation, we get the lambda over the pi. Now we have the famous result. D sine of theta is equal to, when you divide by pi, you get the famous result, 1.22 lambda. Very famous result. And that is given you here, if you want to find the angle sine of theta, you can even do this, 1.22 lambda over d. I mean, either way. That gives you the edge of the disk. And that's very important for purposes of resolution. For example, if you're looking at a disk and you have a central maximum here, then when you find this first minimum, that's a dip, that's going to help you determine your resolution. If you have a star out here and that star is going to be there, the other star has to be sufficiently far away so that when the light travels, it'll fall on this minimum. Otherwise, the two stars, you won't be able to see them. There'll be like two of these peaks. So this star will have its, a peak over here. So the idea is use this this formula, this sine of theta formula times d is 1.22 times the lambda to help you find what that angle is so that you can resolve the two stars. Now, we talked about this earlier in our course when we had this diagram. We had this cool diagram and we were talking about, what's the best pinhole effect? Because if the pinhole gets too small, you're gonna get diffraction, it's gonna mess you up. So if you put here the center and go up to there, that would be how you measure theta. And that's, theta is W over 2 divided by this distance, which we're gonna call F here, which we did in an earlier chapter. But now we're gonna say the conditions should be that this sine of theta is given by this formula involving the airy disk, correct? Because that's gonna give you the place where this will be a minimum, and that's going to be a way to minimize your diffraction effect. So if we do that, let's go ahead and write these out again. Sine of theta is W2 over F, and then since the W is approximately the D in the pinhole camera, we did that approximation earlier, then we replace that D over 2 over F, and that has to be the 1.22 lambda over d. And that means here, when you look at these equations, you will find that the d over 2, by bringing the f on the other side, gets that equation, and then bring the d over as d squared, double the 1.22, and this equation we saw earlier. So I just wanted to touch base with something we did earlier. We pulled that 2.44 out of a hat. And so that's what we should use as one of the criteria. And now you can understand where the 2.44 comes from. Daniel Bernoulli, mathematician and physicist, first defined what is known today as the Bessel function. Bessel himself, who generalized the functions. Now we call them after him, the Bessel functions. And George Biddle Airy, the mathematician and astronomer, and we named the airy disk after him. The airy disk had been pointed out earlier, but he did some nice theoretical analysis on it, and so we named it after him. And here is the airy disk. This is the diffraction pattern from a circular aperture. So if you can think of this as like a star coming in there, you want the other star to be at least over here where this minimum is, so you can start to see like two of them. Beautiful stuff. Bessel functions are scary. Bessel functions, very advanced stuff.